Hello, and welcome to part 5 of the Assembly Language Sound series. Chords. Chords are not always in tune. From the beginning of this series, one of my main goals has been to be able to play multi-part harmony, something you can't do directly from BASIC. And now that we have our music engine running and our horizontal sync interrupts flowing with properly tuned musical pitches through the DAC, it is finally time to layer multiple voices on top of each other. Today we're going to talk about how to do that, and we're going to see how many that I can put together. Did I make it to 4? Well, you'll just have to watch to find out. No, I'm kidding. I'll just tell you. The answer is a resounding... Before we start a follow-up on the end of the last video, I talked about how indexed addressing is a signed operation. And if you don't want to do a signed operation, one way around that is to use the ABX instruction. And in addition to that, since the index I had in the A register, I had to transfer it first to the B register before I could use ABX. Lost Wizard points out that there's actually an easier way to go about this. You don't have to use ABX, you don't even have to use unsigned addition. You can just lean into the signed. What I was doing was starting here in the wavetable and using the index to advance from 0 to 255. But instead, I could have my base pointer start right in the middle, and then I just have my index start from -128 and go all the way up to 127. The basic idea is that when you want to use the full range of a signed value, have your base start in the middle. We can see this in action in the debugger. So what I've done is I've changed some of the self-modifying code to initialize things in a way that would make signed indexed addressing more suitable for what we want to do. So as before, here's our sine wave. It's starting at 4600. And you see it starts at 80, 84, 88, 8C, 8C, then it'll go up to just before 4700 over here. So the two big changes you'll notice are, first of all, my pointer, my wavetable pointer, the most significant byte rather than being 0 is now 80. So that'll be -128, and the base pointer into the waveform rather than being 4600 is 4680. So that means my base pointer is here, and the offset that I'm going to apply to it will be -128, and it'll basically net what I used to be doing, where I would start here and index at 0. Instead, I'm starting here and I'm indexing at hex 80, so it'll move it backward. So I'm going to expect to see the first few bytes out of the sound wave are going to be 84 after I skip past this for the first addition. 88, 8C, 8C, 90, 94, 98, and let's see what we get in the debugger. So I've just fished A out, and A is 84. Next time through, 8C, 8C, 94, 98, 9C, A4. So you can see we've already gone through this first line. Meanwhile, you'll see here that most significant byte has been going up, 8C. So we're going to fast forward a bit. So we're still in negative numbers. As long as the high order bit of the high order byte is 1, we're in negative numbers. Once we hit 0, we're going to expect to be around in the middle. All right, so that has cycled through. Now our offset is simply 1. So we used 1 against X, and we fished out a 78. And sure enough, since X is now pointing here, 1 against X is 78. And as we advance from here, we should expect to see it going down a bit, 74, 70, 60, 68, 64, 64. So if we keep our eye here on the A, 70, 68, 64, 65C, just like we'd expect. And if we keep on going until the wraparound, that'll happen around when this byte gets back up to 80. We'll expect to be near the end of the waveform. So here we're at 7E07. The byte that we plucked out was 7C, which we're expecting to be toward the end of the block. And that is our 7C right there. And then we should cycle back around to the beginning. 7C back up to 80, 84 as we were before. Finally, we get to talk about chords, multiple notes at the same time. I'm going to go backwards a bit and start by showing you what the basic driver program looks like once I have the code in place to play chords. The data that we're going to send to the assembly language routine now consists of 2 notes at a time. This would play a chord of a C5 and an E5, and then after that we would play a chord of an E5 and a G5, and so on. I'm keeping things very simple. I'm not having separate durations for the different voices. The idea is that at any point that we want to change the note, all the notes of all the voices change. And at this point, we only have 2 voices. So this is just telling you at every point what those 2 voices are going to do. In assembly language, I'm going to be storing each chord in a struct called a chord info. And it is ready to receive 4 voices, but I'm not ready to actually try 4 voices. So for now, I'm only going to use voice 1 and voice 2. These are the frequency values for those 2 notes. So these values that we have talked about before, these note frequency values, that's what gets stored in these 2 voices here. And here I set aside space to store 100 such chords. But I don't initialize them here, I allow BASIC to initialize them. And BASIC does that by calling this add chord subroutine. BASIC takes the string of the full chord, it uses var putter to get the address of the string descriptor, and that's what it passes to the routine. So when the routine calls getArg, D will be pointing to the string descriptor. So we move that to X, so now X is pointing to the string descriptor. And then we get the very first byte out of that descriptor, that is the length of the string. And then we skip down to index 2 into that descriptor, and we grab the 16-bit value there, and that tells us the address where the string starts. Song entry pointer is a variable. That variable initially starts where that area of memory starts that I'm reserving to store all the chords, and it will keep advancing each time we add a new chord into that region of memory. So U points to where that chord goes, and we advance through the string 3 characters at a time. And this whole thing here is a loop that picks out each note of the chord 1 at a time. And for each one, we grab the frequency value, which is from this table, and we store that frequency value into that chord info struct. So the first time through, we'll be storing it here at voice 1. The next time through that loop, we'll be storing it at voice 2. And if there were more in the string, which there aren't yet, they would be going into voice 3 and voice 4. And when we're all done, we do a little bookkeeping. We advance the song entry pointer past that chord info, so it's ready to point to the next chord that BASIC adds. And we don't play anything. All we're doing is we're moving those chords into memory that the assembly language routine can access. And we're converting each of those chords into a series of note frequency values that we store in the chord info structs. So it's up to BASIC to repeatedly call that routine over and over and over and over and over and over and over again, and nothing gets played until we finally call play. And before we continue with the code, once again, I wish to thank and acknowledge Simon Jonassen for his chats with me and for sending along this music player, which he co-wrote with Paul Fiscarelli, and which in turn was based on some articles and works done by people from the past, ultimately down to Hal Chamberlain and his article in Byte Magazine. The assembly language code I'm going over is largely based on their 4-voice music player, especially the interrupt handler code. But I do want to mention that I am applying a lot of limitations that they do not have. For example, I don't allow separate durations for each voice. You're just playing a chord, and all of those notes each have the same exact duration, and the duration remains constant for the entire song. So if you want some notes to be longer than others, you have to repeatedly play them over and over again. I'm also not allowing different waveforms for different voices. It's just going to be one waveform for the entire song. These limitations are not hard to lift, but I did just want to keep things as simple as possible, especially since it's interfacing with BASIC. And so with that, let's take a look at the play song subroutine, which is responsible for initializing everything in the interrupt handler so we can get going. This routine does code very similar to code that you've seen before. It sets up the direct page register, sets up the interrupts, it turns on the DAC, and then it initializes a bunch of the self-modifying code pointers that will be used inside the horizontal sync interrupt handler. Once everything is initialized, it just sits here and it loops forever. So the interesting stuff, as usual, is the horizontal sync interrupt handler. Sound out. I'll skip past this stuff for now, and let's go here, which should look familiar. Self-modifying code keeps track of the offset into the wavetable. But we duplicate that over here. We now have two different offsets into the same wavetable. So let's say we're playing our chords using the sine wave. The first voice will have this offset that it keeps track of where it is in its waveform. And the second voice will use that pointer to keep track of where it is within the sine wave. We also duplicate frequency values. So self-modifying code wrote this initially for the very first note in the chord, and this for the second note in the chord. And as before, this is the amount by which we keep increasing that pointer. So if the first note is a high pitch, then we'll be increasing the wave offset pointer by a large amount, thus allowing us to cycle through the wave quicker. And the second voice stores its frequency value here, and that keeps getting added to the second voice's wave offset. And so, for example, if this were a low-pitched note, then it would be advancing this slower, and so it would take longer to get through a cycle of the sine wave. Basically the same stuff we've been doing, just times 2. And in both cases, we rewrite the wave offset so it's now advanced to the next value. And A, which is the most significant byte of the wave offset, is actually the pointer into the sine wave table that we're going to use to pluck the value out, the byte of that wave that we're going to play. And so we use self-modifying code to store that into this instruction here and that instruction there. So far, not a lot of difference. We're just multiplying by 2. Let's see what we do once that bookkeeping is done. For the first voice, we read the byte out of the wavetable that we're going to play, and we store that byte in A. This gets rewritten right over here with the value of the pointer to the table. Specifically, the least significant byte is rewritten there. The most significant byte is just the page where that wave is in memory. So for example, if the sine wave started at hex 4700, this will have been initialized to 47. Meanwhile, this will keep advancing forward and forward through the wave based on the wave offset value. Again, not very different from last time. This is the new thing. Rather than sending A directly to the DAC and then loading A again with what's in voice number 2, we instead take the byte for voice number 2. This value, by the way, same as this. Most significant byte points to the page in memory where the wavetable is stored. The least significant byte is the offset into that table. In this case, it's the offset that's calculated for voice number 2. We add it to A. So whatever the byte value is that we got from the first voice, we take the byte value for the second voice and we add it. This is all that ever happens when you hear chords or you hear multiple instruments playing together. It's just waves adding to each other. That is made very explicit with any digital audio workstation where you have multiple tracks and each track is a different instrument or it's playing different notes. All that program is doing is a bunch of adds. At any point in time, it takes the value of each of the waveforms and adds all those values together to create the ultimate value that ends up getting sent out to the sound card. And that's all we're doing here. We're just adding the two wave values, sticking it in A so that A can be stuck into the DAC. And that's it. We acknowledge the horizontal sync and we get out of there. Well, that's almost it. We should talk a little bit more about this add here. As a refresher, here are the bytes of our 256 byte long sine wave. And as you recall, these bytes range from 0 up to 6 bits being 1 in the upper 6 bits of the 8-bit number. This is the biggest number that the PIA can send to the DAC, and that is a nice cool hex FC. And of course our sine wave at times goes up to that FC. But if I'm adding a byte from this waveform for voice 1 with another byte from this waveform for voice 2, I can easily exceed FC and overflow, and the world will blow up. So what is typically done is, depending on how many voices you need to add together, before this add, you need to scale those voices down. So for example, if I'm adding two voices together, I should actually divide each of them by 2, which can be as simple as shifting them to the right by 1 each, and then adding those scaled down versions of the bytes together. So if I needed to add 2 FCs, I would first shift each one to the right and then add those 2 shifted values together. And that is what I'm doing, but I'm doing it a little bit more behind the scenes because I've got precious cycles I don't want to waste inside this horizontal sync interrupt handler. So instead of letting this be my sine wave, this is my sine wave. I have pre-divided by 2 every byte. So this hex 80 becomes a hex 40. This hex 84 becomes a hex 44. All right, that's not exactly half, but due to round off error and stuff, this is what my little program calculated for me when I divided each of these values by 2. Graphing the actual bytes that are in the wavetable, this is my original sine wave that was suitable when I only had one voice. And this is the version that's been scaled down. Now, no matter what 2 bytes out of this that I add together, I will always stay within range. But there is a price to be paid for this. My Y value range is now a lot more limited, and the sine wave isn't going to have quite as much detail as it used to. For example, you can see there are a lot of repeated bytes here, but the analogous part on this sine wave, there are far fewer repeated bytes. What I've done is I've compressed my dynamic range. I've compressed these Y values down to a smaller area, and so my fidelity is not as good. And we talked about fidelity in the last part. In the last part, we were comparing the differences between an 8-byte waveform and a 256-byte waveform. In that case, we were talking about the x-axis. How many dots can we have before we hit a cycle? And before, we only had 8, so we had a very scattered graph of a sine wave that was only 8 bytes long. Now I get to keep all 256 bytes of fidelity on the x-axis, but on the y-axis it is compressed. And guess what? Every time I add a voice, I'm going to have to scale it down a little bit more and a little bit more so that my sums never overflow. Oh well. Now I'm running this under the MAME debugger because I want to see just how much we're affecting the time with all the code that we've added to the interrupt handler. I still want to make sure that I'm getting called every other Y beam, every other horizontal sync interrupt. So if we keep our eyes here, we're expecting the beam X to be around the same amount each time, and we're hoping the beam Y goes up by 2. So it went up by 2 to 230 to 232. 234, 6, 8, 240. This looks promising. Now we do expect it may skip a lot more when it comes time to move on to the next duration tick or move on to the next chord. So those might be okay. We might not really have much of an issue with that. but we sure would like, while we're holding the notes down, while we're playing them, for this to consistently be going up by 2. And it looks like we're still within range. So while everything seems to be working great, let's add voice number 3. So this section which calculates voice 1, the section which calculates voice 2, we're going to expect to add another section to calculate voice 3, and then we're going to expect to have another add down here. And so here we now have not just 1, 2 wavetable offsets, we also have a third wavetable offset. We have not just 1, 2 frequency values for 2 notes to be played, we have a third frequency value for the third voice. And then if we scroll down a bit, we see we load A with the value of wavetable for voice 1, we add to A the value from the wavetable for voice 2, and we add to that the value for voice 3 from the wavetable, and then we store that into the DAC. Once again, we've had to scale down our waveforms so that they're now, rather than full or half of the dynamic range, they're now each a third of the dynamic range. So now we're starting at 2C and things are a bit more squashed. And in our basic demo, we now have 3 notes playing at once, 3 no chords. So let's see how this sounds. And once again, checking in MAME. Let's see how our timing is doing. So right now we're sitting at beam Y at 38. Hopefully this goes up by 2 each time. 38. Uh-oh. Went to 41. Oh, now it went up by 2 to 43. 46. Uh-oh. 48. Okay. 51. Uh-oh. All right, so it's going up by 2 sometimes. It's going up by 3 sometimes. We're now like kind of between. We're like not quite filling the full interval between 3 horizontal syncs, but we are occasionally more than the interval between 2 horizontal syncs. Ooh! My guess is that when I add the 4th voice, we'll probably now be consistently going up by 3 each time. Ooh. Oh well, let's just do it. So here we are with 3 voices. I'll scroll down a little bit so we'll be able to see the transition. Voice 2, voice 3, and then we start summing. And now we've added our voice 4, again with its own wave offset pointer, its own frequency value, and then down below that extra add to add it in. And let's take a look at our sine table. Even more compressed. This is our quarter height sine wave. As you can see, a lot of duplicated bytes, a lot less fidelity. Here's our basic driver now with 1, 2, 3, 4 notes every time. What does it sound like? And with a breakpoint at the beginning of the very first wave offset adjustment, our beam Y is at 252, 255, 8, 1. We flipped around to the next frame, 2 to 5, 8, 11, 14, 17, 20, 23. This does look pretty reliably to be going up by 3s. It's interesting that everything sounded pretty good.
That sounded good. But if you have a sensitively tuned ear, you will have noticed that the pitches seem to have shifted at some point. And if you have a sensitively tuned coding muscle, you will have anticipated that the pitches should have moved, even before you heard them. Why would this be? We will save that for another time. Next time, we're going to talk about how the player is designed to run the music in the background. And we're going to attempt to run something in the foreground like a basic program while music is flowing in the background. We'll see if we can get that to work next time. Until then, thanks for watching.
Chords, chords, chords.
chords, 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 chords.